Welcome to the Scalable Computing Podcast, joining you from Stanford in the heart of Silicon Valley. In this podcast, we discuss everything about cloud computing, machine learning, and large-scale systems. This season, you'll be joined by world-renowned guests from both industry and academia who have engineered and built some of the largest scalable computing systems in the world. Your host is Dr. Lamia Youseff, a scalable computing leader, one of the early engineers at Google Cloud, and former Microsoft and Facebook technology leader. This podcast is sponsored by JazzComputing, your tech advisor and partner in scalable and ML engineering. Sign up for updates and new episodes at jazzcomputing.com/podcast. And without further ado, let me welcome your host, Dr. Lamia Youseff.
Hello, everyone, and welcome to the Scalable Computing Podcast. It's a pleasure to welcome Viral Shah with us today. Viral is currently the CEO of Julia Computing. He's the co-creator of Julia Langage and the co-author of Rebooting India. Viral and I met more than 20 years ago, almost, at UC Santa Barbara, where he was doing his doctorate degree on computational sciences and very large-scale computational algorithms. And there is a lot of parallels between what he was doing back at UC Santa Barbara and the work he recently doing with machine learning and AI. Welcome, Viral. It's awesome to have you here today with us.
Thanks, Lamia, for inviting me to the Scalable Computing Podcast.
Absolutely. We're really glad to have you today. And jumping right away into UC Santa Barbara days, I was wondering about your motivations early on to work on supercomputers and to work on large-scale computational problems. What motivated you back then? And what was the most memorable lessons that you learned from your research back in the days?
I was always sort of, even before I came to UC Santa Barbara, the thing that motivated me most about computer science and parallel computing especially was the power of computing to explain science. And, we always sort of have, think of science as theory and experiments, and increasingly over the last 20 or 30 years, we think of computation being sort of the third pillar of science. And that was sort of what, drove me towards, towards thinking about HPC and supercomputing and even more specifically in the area of computational science. UC Santa Barbara, as you already know, has a fantastic interdisciplinary curriculum in computational sciences. And back then it was headed by Linda Petzold, the program. And I was very lucky to be part of it. Also, meet with John Gilbert, who actually arrived at UC Santa Barbara after I did. So wow. It took some time finding my bearings because I couldn't quite find the right set of things to work on. But once John Gilbert was there and I started writing MPI and sparse matrix codes, it was, I knew that's what I wanted to work on.
Absolutely. I remember those days when your lab was next to Rich Walsky's lab. And whenever I had a bug in my MPI code, I would run into your lab and ask you, how can I fix that? What I do about this and that? What's the most memorable lessons from back then that you hold on till today?
So I think the whole experience was at UCSB was phenomenal. I know a lot of people often do not enjoy their PhDs either, for a number of reasons. I have sort of the opposite experience. I loved every single bit of it. And, as I'm sure, did you. But I think the most interesting part, the most memorable part of that whole experience for me, apart from playing Ultimate Frisbee and surfing on the UC Santa Barbara campus, was, I had the fortune or the chance of meeting one of my collaborators, Brad McRae, out there. So Brad McRae was an ecologist at NCEAS, which was this UCSB associated affiliated ecology institute. And one thing led to another. We started talking. His codes were extremely slow, and it became what was the CircuitScape project eventually. I really learned the valuable lesson of working with real applications when you're building computational frameworks, computational tools, or so on and so forth, because we always so get busy with our algorithms and our speed up charts, and they all sort of need to go like that. And will the conference accept us or not, and so on and so forth, that we lose sight of who the end users are and who's going to be using these tools and how does it matter. And I had my most fruitful collaboration out, we continued collaborating for a very long time since then. And it until recently was my most highest cited paper, which had nothing to do with parallel computing for the most part. My most memorable lesson from those times. And I think that has helped me a lot thinking about, what we do with Julia nowadays and with various other things that we'll touch upon as we go along.
And you wrote your dissertation on developer productivity, is that right?
Yeah, so my dissertation was two parts. So one was sparse matrix and parallel computing tools that we just briefly talked about. And there was a second part of it, which was programmer productivity, which arose from this program back then, which was run by DARPA, I think, and then it became DOE afterwards. But anyways, it was called High Productivity Computing Systems, and they were trying to design new hardware as well as new programming languages for easy to use parallel computing, so that not only the fancy people in the lab coats know how to program these systems, but every scientist and every grad student could. And I think that was a very interesting program. And I did some work as part of that on measuring programmer productivity. I don't think we did a very good job on that part. But the overall lessons from the HPCS program and the experience of building easy to use platforms and systems is what sort of culminated in my own thought processes and subsequent work on Julia itself.
Speaking of that, of Julia and machine learning languages, as well as the HPC field, I was curious about similarities and differences that you have found between the two fields as both a research area, but also as an industry. What can you tell us about that?
So let's start with the similarities. The similarities are much easier to go for. And I think both areas focus deeply on performance. And at many levels, even the computational kernels are the same. You have the matrix multiplies, the FFTs, and your convolutions, and a few sparse kernels are beginning to make their appearance nowadays. So I would say the focus on performance is a big similarity between traditional HPC and modern machine learning. The second thing is because of this focus on performance and the need for sort of running at massive scale and speed leads to hardware exploration in both areas. So traditional HPC has been driven, over the years. We know the story of all the supercomputers people have designed and used. And there is, I don't know if this website still exists, but there is even this Dead Supercomputer Society website, I believe, which even chronicles the ones that died.
Absolutely.
But it has been this fascinating industry. And, I would say it's like the start of computing itself was because of scientific and numerical computing, right? We created computers to add numbers, right? Not to write documents at some level, like if you go all the way back. And with machine learning now, people are trying all these new explorations with chips and hardware and like new architectures that we would have never seen before. When one of the things that we used to talk about when back in my PhD days was that, oh, wouldn't it be nice if the world moved on beyond matrix multiplication? And then we've had the last 10 more years of matrix multiplication. It's just such an amazing little thing that you can work with. So we've built even more architectures today which do matrix multiplications and convolutions faster, and it's just a fascinating exploration there. The HPC world had its top 500 and supercomputing rankings, and there's all this fun stuff out there. I think the ML space is too new, and so you have things like ML Perf and like a few of these benchmarks and things still, but I still think it's very early days to sort of being able to extrapolate, at least with the modern machine learning. Machine learning itself obviously has this rich history. Third similarity in my mind is, and this is not technical, but this is hubris. I think both fields have shared this hubris that we'll be able to solve everything. If you think of computational science, it's like we will explain all of science that's out there. We'll simulate every little bit out there. Doesn't matter how long it takes. Doesn't matter about the effort. But if we just put our heads to it, and if you have enough compute out there, then we will be able to answer every possible question you may want to ask. And machine learning today has a lot of the same sort of hubris. And I don't mean this in a negative way. I actually think it's amazing that, people are so optimistic about the tools they're building. And I think machine learning has the same sort of optimism around it, that we will be able to solve everything. And we're seeing sort of very interesting combinations of scientific computing and machine learning today, leading to all kinds of interesting new applications and pushing the frontier. And of course, in time, we'll also figure out where the limitations are. Just like you always do with any new field.
Absolutely, absolutely. Definitely, there is a lot of hype and a lot of buzz around what machine learning can do, and that it will solve every problem out there. But it also, as every field, as every research area, it has its limitation.
I thought that the differences are actually the more interesting part of the story. Scientific computing has always been about IEEE 754 and sort of the rigid boundaries of the floating point specification, and machine learning has made us dump all that stuff and think in new interesting ways about how we do floating point computations. Yes. I'm sure William Kahan's not particularly happy about many of the things going on, but I'm sure he's excited with all the possibilities and explorations that's happening. Another major difference, of course, which I think is obvious to maybe most people, is scientific computing tends to be more computationally oriented, whereas machine learning tends to be more data oriented. So working with data, and something. Of course, scientists have always worked with data, but the scale at which, and especially in the e-commerce, internet-enabled world, the scale at which I think some of these modern machine learning algorithms do things, I think, there's that's where both fields sort of have to learn from each other. But I think the most interesting difference is who practices these two fields. And scientific computing has traditionally been practiced by engineers and scientists, right? So, people such as, you and me are sort of more of the minority in the computer science departments. You usually find physicists and chemists and, all kinds of engineers from around like if you go to the supercomputing centers inside the universities, right? And everyone has these clusters. You look at the cycles, who's consuming the cycles on them, it's always sort of traditionally been the scientists and the engineers.
Correct. Yes.
Machine learning is actually something that is practiced more by computer scientists, right? Like it comes, like of course, all the engineers and scientists are also incorporating machine learning, but where you sort of see a lot of it being driven by, it's the computer science department. And these two groups of people do not realize how much they have in common. But they are in silos, and they are both doing their own thing for the most part, even today.
That's a very, very interesting observation for sure, on the differences between HPC and ML in terms of who's practicing and writing codes for each, and who's driving the innovation in each field. So speaking of machine learning, I was wondering about Julia, the early days that you created Julia. What was the gap that you were trying to address early on when you wanted to create a new programming language?
I think this is like, I think the similarities and differences that we just spoke about is exactly sort of why Julia exists, right? It exists to bring people together. So the scientists, the engineers, and the computer scientists, before they spoke different languages, one group used MATLAB, the other group used Python or C++. But both groups now use Julia, right? There's still a long way to go for Julia before everyone's using it. But, our community is comprised today of people from both these worlds. And it also includes people who think about like, hey, I need to figure out Kubernetes and Docker and deployment, but it also includes people who are talking about, I need to, scale my code to supercomputer scale and run it on this weird new chip, that someone released, and so on and so forth. And this is exactly what Julia was meant to do, right? Be an easy to use language that was simultaneously fast and easy. Before Julia, even actually when I remember my days in grad school, that it was always like you write your algorithms in MATLAB. There was no Python back then. There was barely some R, I think. But it was like you write your algorithms in MATLAB and then you rewrite them in C++ and MPI to do anything sort of at scale. And if you step back, it's like, wait, why am I writing the same program twice? That just doesn't make any sense. But it was almost believed to be like a law of nature, like there just can't be these two things together. These last 10 years, we've seen many languages that sort of do performance and productivity. Like you've seen some like Rust in the system space. You've seen Go for like, I would broadly call it the networking space. And you've got Julia in the computational space. And Julia sort of provides both of these things for people of all these different domains to come together so that, they're not affected by this two language problem.
What I'm hearing you saying is Julia is easy, high abstraction level, such that it's not only providing ease of programmability of the models, but also being able to run very fast across different environments and different infrastructure, which is one of the challenges that continue to exist today in machine learning for sure.
I want to just click a button once I write my simple model, at the level that I'm exploring it on my laptop, press a button, and it should just run on the biggest machine I can find.
I love it. How have been the adoption from the community to Julia?
The Julia adoption has been, programming languages are a bit treacherous, right? At some level, like, if most of them do not get adopted, they tend to be research prototypes. The ones that do get adopted have a very long, adoption cycle. And simultaneously, they also have a very long life, right? Because you learn a programming language, you're going to be with it for 30 years, and you're going to learn maybe 3 or 4 that you're really good at. If I think about myself, it's like maybe 3 that I would say I would be very comfortable with. So I feel that Julia, so we've been at it for almost 11 years now. So we wrote our first line of code in 2009.
Nice.
In fact, the conversation started with Stefan Karpinski, Jeff Bezanson, and Alan Edelman, all of whom I met through my scientific computing work at UCSB. And Stefan, I think you might.
Absolutely, yes.
Back then.
Stefan, another colleague from UC Santa Barbara and currently at MIT, I believe.
Currently a co-founder and also CTO of Julia Computing, so not at MIT.
Awesome.
You all sort of left the MIT research team in around 2015 when we founded the company. It's just difficult to build a real product outside, inside the university. And at some point, we just decided that we needed to focus on getting Julia into the hands of users and companies, and that was not going to be possible in an academic environment.
Very true, very true. So speaking of that and of the community of Julia, I'm curious about the open source community or building an open source language. How did you find managing an open source community and interacting with the open source community in general? How do you attract and motivate contributions to the open source code, as well as making sure the community is always motivated and always supportive of changes?
So we are now at about, my estimate is 500,000 Julia users out there. So if you look at sort of the Julia Slack, there are 6,000 people on it. The Julia Discourse, I believe, has over 10,000 people. And the total number of downloads of Julia is over 20 million today. But those numbers kind of don't mean a whole lot because there's CI and all kinds of things. But it's still a very large number of people. Like someone's downloading Julia to do some useful stuff all the time now, right? Like every second or something.
Yes.
And it's a challenge to maintain a community. We've seen many communities in the past around other systems, and some of them are very toxic. I feel like they're not welcoming. They're not, or sort of there's always this one-upmanship going on in some of the communities. And from a very early stage, we decided in the Julia community that we wanted it to be a nice place where people can sort of, feel safe about participating, about voicing their opinions. And it's like, not being nice is unacceptable. Like, that's just how it is. And I think I would sort of give the credit to Stefan for the large part on sort of setting that tone very early on. And I think it has worked out very well from us. Of course, now we have a lot of community moderators and many others who bought into the larger sort of vision of Julia. I think so to your question about how do you sort of, keep the community going, right? And how do you manage it? Well, one is, of course, there's the governance and having all these, we have the Julia stewards, we have, moderators, we have sort of this multi-level system of making sure that everything is run well and in a fair way. And we have a community code of conduct that we are very serious about.
Love it.
So the other thing is, how do you get the contributions, right? That was sort of the second thing that you mentioned about the community. So, you can have a nice community and all these rules and governance, but if no one wants to come, then it's kind of not so good. And I think there are two parts to it, right? One is the overarching vision, right? Like that we as the core sort of creators and developers of the Julia language have set out, right? That we want to solve the two language problem. We want something that is fast and easy. All the things we talked about, right? So there is this vision that unites everyone from a variety of diverse different fields. But then the other part of it is the design, right? That if it's just too difficult to contribute, if it's too difficult to understand the code, if it's too difficult to write a package, no one will do that. So the second part of the thing that complements the vision is the design. And I think the language design, the fact that you can start out in Julia as a user and get the same level of high performance as like an expert who would have written this kernel with handcrafted assembly is liberating, right? Like a lot of people come with an experience from Python or R. They just have not seen that level of performance before. And people who come from C++ are like, oh, wait, I can get this level of performance without sort of going through, this large amount of code. And you see that people start out by being users, and then slowly they become a contributor, they write a package. And before you know it, they're like, submitting like bug fixes to the compiler itself. And we've seen people make that entire journey, and it's just, so satisfying to have seen that happen.
That's super awesome to hear, Viral. I'm curious though, as the CEO of Julia Computing, what keeps you up at night?
Oh, that's a tough one. That's the one I should have said I don't want to answer. Actually, lots of things. I mean, it's like running a company is not something you train for or you learn about, right? Like, we went through a PhD program, we know how to solve problems, scientific problems in a logical way. But running a company is not about, logic. It's about, or it's not even often rational, right? Like you're working with people and, customers, and everyone has their own sort of, reason why they're participating. And there's just, it's a lot more ill-defined in many ways. But I think we have a fantastic set of people who've come together to, form Julia Computing in what it is. A lot of core contributors to Julia, united by a common vision and desire to make the best computational tools available to everyone. The thing that particularly keeps me at night are two things, actually. So one is, are we solving the right problems? Are we doing things that matter in the world? Because that's sort of the reason of our existence. And the second is, do we have enough money to keep doing that? And that's sort of the two things I particularly spend a lot of my time worrying about.
I totally agree with you. It's not easy to run a company. All right. So coming quickly to the lightning round, are you ready to play?
Let's start.
Let's play. So the first one, what's the most surprising use case of Julia you have seen so far?
Web technologies, things like Pluto, Franklin, WebAssembly. Just never thought that people would use Julia for building websites.
Cool. What's the most impressive open source software or startup that you have seen recently, Julia related or not?
I would say, so one of the companies that we are sort of very closely working with called Pumas.ai. And it is a company that is using Julia in ways that we haven't imagined in order to build the best drug development pipeline, starting from sort of, clinical trials design, taking it all the way to FDA approvals.
Wow, interesting.
You know that they're really using Julia because they often find compiler bugs.
Nice. If you can describe Julia in one word, this word is?
Fast. It's, for me, I think fast matters more than many of the other attributes associated with Julia. But at the end of the day, if it's not fast, if it doesn't use the hardware to the max, I don't want it.
Agree. The future of AI and machine learning platform is?
I think that's an easy one. I'm gonna just say Julia there.
Nice. Love it.
But I do honestly believe that it is because, the scientific computing world has found its languages to work with. The machine learning community is still not found that language, and they're, stuck with Python for the most part. And I think Julia is sort of the way forward.
One lesson machine learning field should take from computational sciences and HPC is?
I'm gonna say that famous quote that winter is coming, right? what we've learned from the supercomputing and HPC space is that it has its ebbs and flows, and so you got to figure out what works, what doesn't work, and then how it fits in the larger scheme of things. I think machine learning is at an all-time high right now, but we know that these things are mean reverting processes, and don't be disappointed when that happens.
So today, Python and R are machine learning languages that are shooting themselves in the foot because?
I mean, it's a tough one to answer, like why they're shooting. I mean, the fundamental answer is they're shooting themselves in the foot because they're slow. But what makes them slow and what makes them not suited for machine learning and the kinds of things we want to do is at the end of the day the language design, which does not allow for easy automatic differentiation, easy performance targeting new hardware. And this sort of single-minded focus on Python is the answer to everything, I think is actually hurting the larger adoption of some of these technologies in the rest of the ecosystem and the rest of the sciences and so on and so forth. So I really feel that the machine learning community does need to define a new set of tools and languages that it works with for the long run.
Viral, that was an awesome conversation today. Thank you for taking the time. We covered your work at UC Santa Barbara and how it led to Julia and designing the Julia computing, and then your current role as a CEO of Julia and what keeps you up at night. But also we covered the differences and similarities between HPC and machine learning, and then managing and building an open source community. That was a very rich conversation. Thank you very much, Viral, for taking the time.
Thank you, Lamia, for having me on the podcast.
Sign up for updates and new episodes at jazzcomputing.com/podcast.